This is Introduction to 16.8 and 16.9 in Thomas's textbook and section 16.5 in the Stewart's textbook. In this lecture, we will define two differential operators, namely the curl of f and divergence of f. Remember that del operator was a vector whose x and y or x and y and z components were blank partial derivatives, correct? These are blank. So they don't mean anything unless they're applied to a scalar function either in R2 or R3. So these are the definitions of these differential operators. The next one is called curl of f, which is del cross f. Del is that operator, remember, gradient operator. So if you form this 3 by 3 determinant, so what happens is the first row is ijk, the second row is the blank what? Partial derivatives, and the third row is what? Is the components of the vector field in R3, namely P, Q, and R. When you perform this determinant, the answer comes up a vector. In other words, the curl of f is a vector. On the other hand, the divergence of a vector field is del dot f. In other words, this is a dot product. And if you take the gradient and this operator, which is also known as nabla, and dotted with f, then again, f is pqr, you get partial of p with respect to x plus partial of q with respect to y plus partial of r with respect to what? Z. But notice the answer is a scalar. So the divergence of a vector field is a number. The curl of a vector field is a vector. So please make sure you keep these in mind. So let's do an example to see what's going on here. Suppose you have a vector field in R3, okay? And imagine this is the P, okay, X component. This is Q, Y component, and this is R, Z component. Question is, find the curl of f and divergence of f. So to find the curl of f, you have to form this 3 by 3 determinant. Okay, so the first row is ijk, the second row is blank partials, and the third row is pqr. Make sure you follow the order, yes? So if you expand this, you would get I times what? Partial of this guy with respect to y minus partial of this guy with respect to z. So that's where this has come from. Don't forget there is a minus sign, j, and that would be partial of this function with respect to x minus partial of that function with respect to z. Then you have k components, so that would be partial of what? This function with respect to x minus partial of that function with respect to y. When you take those partials, you end up with minus e to the y cosine of z minus e to the z cosine of x minus e to the x cosine of y. Notice the curl of f is, at the end of the day, what? A vector. On the other hand, the divergence is a scalar. What you do, you take partial of p plus with respect to x, partial of q with respect to y, and partial of r with respect to z. When you do, notice this is not a vector, it's a scalar. It's not a vector. So that's what divergence of a vector field is. If f is a vector field defined on all of R3 whose component functions have continuous partial derivatives, and the curl of f is 0, then f is conservative. So there goes a nice test to see if a vector field is conservative or not. Check and see if its curl is equal to 0. Okay, if you remember, the test we used in previous sections was to see if what a vector field in R2 is conservative or not. Remember, we said you got to take the partial of this guy with respect to y and see if it is equal to partial of this guy with respect to x. So now that we know what curl is, let's see where this is coming from. So if we let what the vector field to be PQ, there is no z, so the z component is what? Is 0, because remember the curl has to be applied in R3. So, and you form this what? Determinant 3 by 3. Remember, you always have to come up with 3 by 3 determinant, because the curl only applies for functions what vector field in R3, yes? So it has to be function of x and y and z. So this is what you get. But remember the what? We just learned the fact that in order for what vector field to be conservative, its curl has to be 0 vector, not 0 number, 0 vector. In this case, that 0 vector happens to be what? 0, 0, 0. So what you do, here is the 0 vector. Set these guys equal to each other. And what happens is, well, 0, so we got to do some matching here because you got a vector on the left, vector on the right. For these two vectors to be equal, the corresponding what? Components got to match, right? So this guy got to match that 0, and this z component got to match that 0. When you set that z component equal to 0, you will get what we had before. So that's where it's coming from. Once again, notice the 0 vector in this case is 0, 0, 0. Remember, curl of f, the operator curl only applies for functions of what? 3 variables, R3. If you have what? Vector field in R2, then set the z component equal to 0. Similarly, if the vector field is what? In R3 with R not being with PQR, remember we had these 3 ratios, remember? So if you compute the curl of f, you know, these are the partial derivatives, this PQR, you get this. But remember, if curl of f is 0 vector and 0 is 0, 0, 0, then f is considered to be what? Conservative. Remember, this was the test we had to apply in order to see a vector field in what R3 is conservative or not. In other words, we had to satisfy 3 equations and make sure they all satisfied. The question is, where did they come from? Well, that would be the curl, right? If you set this vector equal to 0, so that means you have to set each of these components equal to 0, correct? Like so. Okay. And guess what? Lo and behold, when you set these guys equal to 0, so you get the first fraction, second fraction, proportionality, and the third proportionality. And that's basically where these ratios, equality of 2 ratios are coming from. So the bottom line is this. If f is conservative, then you can bet your money that the curl of f is 0 vector. So keep that idea in mind, super important. Now the question is, where does the tidal curl come from? And divergence. Why do they call this curl and divergence? Turns out the word curl comes from the fact that if f represents the velocity field in a fluid flow, particles near point what? XYZ in the field tend to rotate about the axis that points in the direction of the curl of f. In other words, the reason they call it curl because it has to do with rotation. Okay, about the axis that points in the direction of the curl of f at point what? P. And the length of what? Of this curl vector is the measure of how quickly the particles move around the axis. So what that is the following. If the curl is 0 at that point, then the fluid is free from the rotation. So when the curl is 0, that means what? The vector field is what? Conservative. In the context of rotation, there is no rotation. That's what that is. So the fluid is called free from rotation at point P, and it's called irrotational field or irrotational fluid. Do you see it? So therefore, this has to do with something like we refer to in engineering like a local rotation, not global, it's local. So if you have a flow of the fluid at some specific point in the flow, you can measure what? How much rotation do you have in the fluid? And when we say fluid, it could also mean gases and all that. So fluid is just a general term. So to say the curl of a vector field is 0, and if that vector field represents the velocity field in a fluid flow, that just means there is no rotation. So the what? The fluid is called irrotational fluid. So it has no rotation. So the question is, where does the divergence, the tidal divergence, come from? And that's like, then again, if F is the velocity of a fluid or gas, then the divergence of F represents the net rate of change with respect to time of the mass of the fluid or gas flowing from the point XYZ per unit volume. In other words, divergence of F measures the tendency of the fluid to diverge from a point. Diverge means what? To get away from a point. That's what divergence is. However, if the divergence of a vector field is 0, 0 the number, not the vector, then field is said to be incompressible. That means you cannot compress what? The field. Let's say with what? Like fluids. They're not compressible. Gases, but fluids are not. However, if the divergence is positive, you have net outflow through every circle. And the point which what? The flow diverges from, it's called a source. So this is also known as outflow flux. If the divergence of vector field is negative, that means you have a net inflow through every circle. So the point which what? The flow points to is called the sink. And this is kind of like inflow flux. You will see a picture in a minute. If the divergence of a vector field is 0, 0 the number, there is no flux. So the flux through every circle is what? 0. Remember what flux is? Amount of mass per what? Volume. That would be like volume of the fluid per unit time, which crosses a surface or a curve. Remember, we talked about flux in previous chapters. Here are some interesting graphs for you. Notice here's the vector field, x comma y. The divergence is 2, so it's positive. So therefore, point P is called a source. Notice the field is divergent from the what? Point P. Now remember, F was gradient of what? Scalar function F. Remember, we called that potential function. If you find the potential function, you get x squared over 2 plus y squared over 2. But if you draw the what? Level curves by setting this guy equal to k1, but then multiply both sides by 2, you get y squared plus x squared equals k. So that would be a bunch of concentric circles. That's where I got the circles from. But if you notice, if the divergence of the vector field is positive, then the net outflow what? Through every circle is shown in this diagram. So we have outflow flux. So therefore, this point here is called a source. Okay, so this is like a source, like, let's say temperature is considered to be a source because wherever the heat is dissipating to everywhere in the room, so that point is called a source. On the other hand, if the divergence of a vector field, in this case the vector field is negative x, negative y, the divergence is -2, so this point is called a sink. Notice all the what? Vector fields, all the vectors pointing towards the point P. So that's like a sink. That's what it's called, sink. Then again, if you solve this, you would get the same what? Contour map, which is x squared plus y squared equals what? A bunch of concentric circles. And notice we have net inflow rate towards the what? Sink. Do you see it? So that's what happens when the divergence is negative. If the divergence is zero, then the field is called incompressible. That means you cannot compress it. And this is how it looks like. Okay, suppose the vector field is what? This is like, let's say, x comma negative y. So the divergence is zero, so the field is called incompressible. You cannot compress it like, water. Okay, then again, you get the same, what? Contour map, but notice there is no flux here through every circle. Why? Because some of them are going towards the source, some of them are what? Some of them are, acting like going towards the center of these circles. The other ones are what? Coming out of the circles. So what happens? They cancel each other out. So the net flux is zero. So there is no flux through the circles at any point in this field. And that's why this is called incompressible vector field. Thank you.